I'm very grateful to Peter for invitation, and I'm especially happy to talk here because my journey into G2 in general and new wave functions, the L functions with non-unique model in particular started here in Princeton some 12 years ago when I was postdoc here. So although the central integral that I'm going to discuss eventually will be the integral on the exceptional group G2, I will try to keep it just as one of the example and to discuss a general approach for integrals with for L functions which unfold with non-unique model. So let us just start with a general setup. Let F be a number field and G be a algebraic reductive group defined over F, and then we denote by LG its dual group, complex dual group, and we fix a finite dimensional representation rho for the dual group. Okay. On the other side, let us consider an irreducible representation of the adelic group GA. Irreducible representation of G of A. So far, no automorphicity is assumed. And since it's irreducible, we know that pi is tensor product of representation of local groups where almost all of them are unramified. So for almost all V, place V to the representation pi V, there corresponds its Satake parameter, which is a conjugacy class in a semi-simple conjugacy class in the dual group. So we shall denote it like that. And given this data, we can define a partial L function for data pi and rho, which would be a product of local L function. So local L function at those unramified places will be defined as the inverse of the characteristic polynomial of rho of the Satake parameter. So this is a rational function in Q minus S, where Q is number of elements of the residue field, Q nu. And the L function, the partial L function of pi, is defined to be a product of the local L functions for almost all places. Okay, so this is, I would say, for almost all places where S is a finite set. Okay. So this is the main object we will speak about. So far, it has been defined for any representation, any reducible representation. So we do expect special properties of this function when pi is automorphic. So general expectation that if pi is automorphic, then this this product converges for large S and has meromorphic continuation for the whole plane. Okay, so then has meromorphic continuation. Moreover, its poles can characterize our representation in some nice way. For example, show that the poles of L functions could, for example, characterize pi as an image of functorial lifts, and so on. So say important information about pi. So carry poles, I will say vaguely, carry info about pi. Moreover, properly completed, if we find a nice and good way to complete, to define LS functions also at the rest of the places, at ramified places or Archimedean places, then this function should also satisfy a nice functional equation. Okay, so properly completed. Satisfies functional equation. I will not speak about part 3 at all, but only about 1 and 2, as we will talk only about the partial function, not the completed function. Okay, so all this expectation should hold when pi is automorphic representation. So to prove this, it is reasonable to use the realization of pi as an automorphic representation, physical realization. Okay, so to prove 1 and 2, there is a method which is called integral representations, or Rankin-Selberg integral representation method. And here is the idea. Pi is, we fix an embedding pi into automorphic form of G. And let's consider an integral. Okay, so saying some vector into actual automorphic function, and consider some integral which would depend on the vector phi, also will depend on a complex variable s, and maybe some auxiliary data. In the middle, in a minute, I will give examples, actually many examples, and whose analytic continuation or meromorphic continuation and poles could be, whose analytic behavior can be actually obtained. Okay, so in a second, when I will give examples, I will see where we get this meromorphic continuation and other stuff from. Okay, so this is explicit example. This is not a this is explicit integral. It is not given as Euler product at this point. So whose analytic behavior can be studied. I mean, not so. And then try to relate this to the L function. Okay, so in a minute I will say what it means. And roughly speaking, it should be equal for certain data. Okay, relate it to the partial L function. Okay, so let me now give an example or several examples which I would like to proceed with till the end of the lecture. And the example which I will eventually talk about will be one of those, but the pool of examples is quite general. So here is a general example. So let G be a group, okay, and assume it is embedded into some bigger reductive group H, okay. So this is the reductive group H, who in turn has parabolic subgroup, okay. So having H and its parabolic subgroup, say maximal, okay. We can consider an induced representation from trivial character, from the trivial representation of the Levy, so degenerate induced representation, say delta PS, okay. Trivial representation times a character which depends on S, and realize it automorphically using Eisenstein series. So every section F goes to the Eisenstein series of F, S, H. Okay, so this is familiar construction, and having this Eisenstein series on a bigger group, let us consider the following integral. So this integral depends on a vector from our representation, complex variable S, and a section in this induced representation. And this integral is simply integrating our cusp form against this Eisenstein series restricted to the smaller subgroup. F, S, H. Okay, so note this integration is here. Note that if pi initially was a cuspidal representation, that this functions rapidly decays, and there is no problem convergence of this integral. Okay, so now when I say that the properties or analytic properties of this, sorry, this is a G. So you start with a G. Oh, I'm sorry. Yeah, of course. Thank you. So when I told that the analytic properties of this zeta integral can be studied, in this particular case, they can be obtained almost for free because of the powerful theorem that this Eisenstein series does have an analytic meromorphic continuation for the whole complex plane. And also has a functional equation. So, but at least the meromorphic continuation of this, the whole integral, doesn't need to be proven here. Okay, so you might ask what kind of examples exactly we are looking for. So let me just give you several ones. Maybe among all the examples of Rankin-Selberg representation, this will be not the simplest one because of the form that I have chosen, but still they are not so complicated. So let me eliminate several examples. So first example is a so-called doubling integral. This is the case where G actually a product of two identical groups. Let me just, as an example of classical groups, let me just an example take, say, sp2n times sp2n, and this is embedded into H, which is sp4n in the familiar way when P is the Segal parabolics, is Segal parabolic. In this case, this integral can be formed, and it eventually represents the standard L function for the group sp2n. So another case would be so-called triple L functions when G is actually the product of three identical groups, GL2. Okay, we can take it to be, for technical reasons, we take this group GL2 cube, the subgroup of the elements who all have the same determinant. It's not essential. It's essential only to show that this product sits inside the group GSP6 in a quite similar level, right? Here, the 4n-dimensional symplectic space can be broken as a sum of 2, and here the 6-dimensional is sum of 3 symplectic spaces, and again P is Segal, so this is famous triple product integral. Third example would be of the pioneers in the method of the new way method, Pitetsky, Shapiro, and Rallis. And here is their case, sp2n. Actually, in this case, H is also sp2n. However, obviously, when we integrate a function, a cusp form against Eisenstein series, we get 0. So in this case, we integrate the cusp form against the Eisenstein series and another function on a bigger group, which is the theta function on the group sp2n square. Restricted to sp2n. Okay, so in this case, we integrate not just the Eisenstein series, but Eisenstein series times another automorphic function on a bigger group. And finally, the example which is supposed to be the topic of my talk is the case where G is exceptional group G2. This is, and H is yeah, this is a usual Shimura integral, exactly. Well, I mean, to be honest, this integral is properly defined only when n is even, because you don't want to consider functions on the Metaplecki cover. But yes, essentially, this is a generalization of Shimura integral. So 4 is G is G2, and H is a simply connected group of type D4. So just to those of you who are not familiar with G2, if you have the D4 group, so this is SO8, it's simply connected cover called spin 8. If you so you have triality, there is a group acting on the vertices of the Dynkin diagram. So after identifying them all, okay, the fixed point of this action, so this vertex stays the same, but those three vertices sort of glue together. And this is the group, this is the Dynkin diagram of the group G2, so you can see visually how it is been embedded into D4. But that's doesn't matter for the purpose of the talk. And it has the Heisenberg maximal parabolic subgroup whose levy is GL2 cube. Okay, so these are 4 examples, and actually they are all 4 are different, have some different features, which I will again explain in a minute. Okay, so this is the example. Now, how shall we proceed into? I explained already that its analytic behavior follows from the nice analytic behavior of Eisenstein series, but now remains the question: how shall we relate it to this L function? And the first step is what's called unfolding. Unfolding is a completely formal procedure of dealing with such an integral, looking at S big, replacing Eisenstein series by some whatever it defined, and proceeding quite formally. And actually, in this case, the steps are very naive. I mean, sometimes unfolding could be complicated, but in this case, just very quickly, you arrive to the following expression. So this will be an integral of G over A mod some subgroup of G R over A. So as you see, the domain over which you integrate is so-called Eulerian. Namely, it's a product of the local. Well, you know, you want that G has an open orbit in H mod P. Yes, that's what. Of course, it won't work like in complete generality. It's just okay. So what do you have here as an integrand? Let me explain in a second. Okay, so this function fs will be an Eulerian function, meaning it's a product of local function, okay, which has which knows nothing about your original representation pi. Whatever this function involves all come from the information from this section. Okay, so this function doesn't have to do anything about pi. What remains of pi is all here. So what is this lambda? Let me see. Okay, so let me just copy it here. Or maybe I will not. I'll just write that lambda of phi is generally, so you want that both of these functions will be RA invariant. So in most of the cases, it's R of A integration over R of A of your function. Okay, so this is a functional, which gives to any phi this number. And now if you allow to G to X on phi, then it gives you a function. So this function is called a model for the following reason. This lambda obviously belongs to the home space of pi of C. I'm sorry. It belongs to the home space, which is by Frobenius reciprocity is home G of A pi induced, right? Basically, this lambda realizes pi in the space of the function G mod R, and hence it's called a model. So this model could be unique. This is the case where this home space is one-dimensional, or could be non-unique. Okay? So generally, we say that lambda is a model, unique if this home R of A pi C is one-dimensional, and non-unique otherwise. Okay, so what would be the models in those examples? Okay, actually all four have different models. Okay, so in those examples, in example one, the model that we see here would be just inner product. So if in the case G is sp2n times sp2n, so any function is basically a product of two functions. Okay, so you have representations pi1 here and pi2 here. In this case, lambda of f pi1 times f pi2 would be just an integration over sp2n. So the subgroup, which is R, which it is sp2n diagonally embedded here, f pi1 of G, f pi2 of G dg. In particular, so of course, this lambda belongs to home space of pi1 times pi2 into C. So in particular, this doesn't vanish if and only if pi1 is pi2 contragradient. All right? So it's not 0 if and only if pi1 is pi2 contragradient. So in case this model is 0 identically, so it could happen that such an integral will just always vanish. What it means that that integral vanishes. So this integral just, in the case our representation doesn't support this model, okay, the integral representation just gives 0, okay, no information. So to somehow to relate this integral to our L functions, we should make sure that our representation does support this model. Okay, so lambda is a model. This is just a inner product in the first case. In the second case, lambda is so-called Whittaker model, home n pi s psi, where n is the maximal unipotent radical, or well, yes, it's a unipotent radical of the Borel subgroup here. And as the Whittaker model is always unique, this is a general theorem for any group, and for a given character, of course. And the representation that supports is called generic. Okay, so for GL2, all cuspidal representation, even for GLN, are generic. So this integral will work for all cuspidal representations. In the third, as well in the fourth case, integral unfold. So let me write down that this is unique model, and this is also unique. However, in the cases 3 and 4, the model will belong to the home space of pi, again with the character, and the functional has invariant properties under certain unipotent sum group of some parabolic. So in third case, this is the unipotent radical of Ziegler parabolic, and in the fourth case, it will be the unipotent radical of Heisenberg parabolic. Okay, so both of them are non-unique models. Okay, so this case has been treated in Pitetsky-Shapiro in the late 80s as was called a new way to treat L functions. So far we are just in a preliminary step of the unfolding. Let me just remark that, note that difference, so that functionals here could be parameterized by some arithmetic data. So the Levy group of this parabolic acts on UA, hence giving rise to the equivalence between different characters of U, and basically the equivalence classes are parameterized in this case by quadratic forms, okay, and in this case by cubic forms. So, and when the question arises whether given representation does support this model, this Fourier coefficient, then, so meaning whether for all the representations such an integral will not give us identical 0, okay, and the answer is affirmative, namely, yes, for any representation of SP2N, there exists a quadratic form such that the function, there exists some function in the space that supports this Fourier coefficient, whose Fourier coefficient is not 0 with respect to this quadratic form. And similarly, for any cuspidal representation of G2, there exists a cubic form such that pi supports this Fourier coefficient along the cuspidal, along the Heisenberg group, where this psi corresponds to this cubic algebra. This is extremely important because unlike for GLN, the representation of G2 or SP2, not all cuspidal representations are generic. All right, so if you start with the integral representation that unfolds with Whittaker coefficient, this won't be enough because some representation will miss it. The integral will be 0. But so it's important to make sure that every cuspidal representation is captured in this way. Okay, so now, very well, assume we got this. How shall we proceed from this point? Now I remind you that we try to relate this function to the L function. Okay, so normally before Pitetsky-Shapiro and Rallis, the traditional method went into the following step. First of all, if this model is unique, namely this home space is one-dimensional, then this functional is a product of local functionals. Okay, so we show that this shows that this integral is Eulerian, namely a product of local ones. So I keep the notation for phi nu to, I think of them as just a vector in the representation, so such that the phi is pure tensor vector, corresponds to this tensor product of local vectors. Okay, so this would follow immediately for non-unique, for the integral with unique models. Okay, so immediately for when model is unique. The model is unique. Well, and second step would be to show, so this is a product of over all places. And the second thing would be to show that at unramified place, this local integral, how shall we call it? Sticking in what is called spherical data, namely sticking in all the vectors which are k-fixed at almost all places, just equals to, which is, let me remind, this will be just g of f, r of f, nu, this local functional. Okay, so since this function is unique, you also hopefully have a formula for it, and doing many calculations, eventually show that this is the L function, direct computation. Okay, so first of all, being not very illuminative, it's obviously, this method is obviously restrictive for the functions with non-unique, for the integral which unfold with unique model. So now I'll try to convince you that all the questions of whether the model is unique or non-unique is completely irrelevant here. And this integral, which this equality, which depends from the representation pi on both sides, since it holds for all the pi, this variable pi should be eliminated from the equation. Okay, so I will elaborate on this on the moment. So this was traditional way. Now let me introduce this new way idea. Any questions?
Second, the right-hand side doesn't depend on f.
On? This f?
No, yes. Like the left side has an f, but the right side.
Okay. This f incorporates f small f. So this f actually, as I said, it depends on the small f. I mean, this big f is a trace of the trace, not in a mathematical sense, like after unfolding, we'll get a function f, which depends on this small f, doesn't depend on the representation in question. Okay, so.
I think what he's probably saying is the left-hand side seems to be tricky depending on the choices. There's a normalization. Okay. The right-hand side. Yeah, the right.
You mean the normalization of the function?
No. The right-hand side is an L function, but it makes no mention of f. So is there a normalization way?
Oh, you mean, how comes that this doesn't depend on f? That's because I choose spherical data here. So. Oh, okay. Yes, spherical data, and of course, yes, I want to take f of 1 to be 1 or whatever is appropriate. I mean, it's could be different in many cases. We have to introduce. No, this is a local L function.
Oh, that's a local.
That's all.
On Rami. Okay.
This is so this step is called Eulerian part.
Put pi newts, okay.
I did. So this is called unramified computation. Just to make sure. Okay, so two parts: Eulerian, showing something is Eulerian, and second part showing unramified computation. And hence, of course, you see that Z is indeed. Okay, so let me just one small remark from here. So from these two steps, it shows that our ZF phi is a product of local zeta. Almost all of them is partial L function, right? And we also have a product of so-called bad places, right? Local factors. But those carry only finitely many information, so this is just finitely many multiples. So this should be controlled separately. So when doing by control separately, we have to show that we can choose data such that for any S0, we should be able to choose this data such that this part is holomorphic around S and doesn't vanish. Okay, so this is called what's called ramified computation. Okay. So should be controlled. Controlled meaning no poles, no zeros. For some data. Okay? Because that's enough for us. And hence, since this is good by construction, so this has meromorphic continuation, and the poles, and which is more important, I think, so also as important, that the poles of L functions are contained in the poles of Eisenstein series, whose poles are, especially if we talk about degenerate Eisenstein series, are easy to control. Okay? Everything is relative, of course, easy. Okay, so now we are going back to this new method. New method says the following. Let's ignore the first part, Eulerian. We cannot, since our functional lambda is non-unique, there is no way to try to show that this is a product of local functionals. Okay? Instead, what we shall do is go straight to the unramified computation, ignoring the first part. So what does it mean? We write a candidate for a local integral. Okay? So we start right away with, so we first sort of do unramified computation and then show that the whole integral is Eulerian, almost Eulerian though. Okay, so new way. We start with a integral, local integral, candidate, GF0 F nu GS dg. Okay, and try to analyze this. Now question arises. Actually, this delta belongs to the some home space, which is not one-dimensional. It could be infinite dimensional. So which functional should we take? And the answer, it doesn't matter. Whatever you take, this integral will give us up to normalization the L function. Okay, so this is a sort of bit surprising statement from the beginning. So that's what we want to prove. Okay, so first of all, assume we proved that. How shall we proceed? How to show Eulerian part? Okay, so let me just stress for any lambda in this home space. Okay, So assume we prove that this is proven. Now let us see how the global zeta function factorizes. Okay, then looking at g of, so instead of looking of integral of g of a mod r of a, let us look at the g of what's called f omega. So we look at the group subgroup of adeles where we multiply over the local groups over a finite set omega. Okay. And then we shall increase this omega all the time. So as you see, if we add to this omega just another place, then doing this calculation, I mean our f is Eulerian, so f of omega union v will be a product of f omega times fv. Okay, fv times f omega. So applying this computation, you see that this kicks away the factor, the unramified factor for v with the initial factor that we had. Times whatever we have before. Now taking the limit over omega, f omega, we get the statement. So this means that eventually our integral over adeles equals to the partial L function times some factor which we had at all bad places. So the integral is not exactly Eulerian. It's not product over all bad places or over all places. It is product over good places, over unramified places, plus a bunch of the bad places all stuck together. Okay, so in this case, we see that this is what we want to show, L pi rs times something which, again, this will be an integral over g bad places, fs, rfs. And whatever we have here, everything depends only on the finite number of places, finite data. Okay? So again, this should be controlled separately. This is not very difficult in the concrete cases. Since this function admits meromorphic continuation, its poles could be studied through the study of poles of Eisenstein series, so we have complete information about L. Okay, so now I have to hurry to actually, this is the core of the talk, to explain why this identity should be true. Okay, so here is the explanation. The general idea is, as I already mentioned, since this equality should work for all lambda and all pi, okay, we want to eliminate both from the equation. So like if we have ax equals bx for all x, we better have a equals b. This would explain at least the identity. Okay, so our goal is to transform this identity into identity between two functions. Each of them doesn't know anything about pi and lambda. And here is the method. So first of all, let's look at leaving the left-hand side untouched. We look at the right-hand side and remind us So starting with the following well-known identity, that such an L functions can be written as trace of symmetric n powers of rho of t pi, okay, q in the minus ns. So this follows just from the decomposing the factors into the rational factors into the geometric series. And in this way, we can define so-called generating function for the function rho. Namely, recall that we have a Satake isomorphism between this and the representations and the representation ring of the dual group, okay, which can be by linearity completed to the isomorphism of the power series. Okay, so looking here as at the element which is the sum of symmetric n power rho q minus ns. Okay, there is a corresponding element, so power series whose coefficients are elements of Hecke function. So for far formal, we can show that this it should converge for S large and furthermore, but these functions we call it delta rho gs. So this is what is called generating function. In what sense it is generating? In the sense that whenever we integrate pi of gv for any unramified representation pi, when we integrate, take a convolution of it with rho, this will be exactly as taking the trace of this part of this side on the element which is t pi. This is the meaning of Satake isomorphism, and hence giving our L function v0. Okay, very good. So this is such an identity. This delta is quite difficult to find, but it's definitely formally exists. Okay, sometimes it's easy to find, and then we are in a good shape. Now we want to apply our delta, whatever it is, to both sides. So here is integration over g, and let us apply it as not the lambda to both sides. We of course get such an expression, and now let's remember that our lambda has invariance properties under R. Okay, so we can factor this into integration of g mod R, lambda pi of g v0. The integration, I mean, this thing doesn't depend on R. However, here we should average our functions over R. So breaking our integral over g as integral of g mod R and R, okay, we eventually get this. G. Very good. So this equals the L function. Okay, and now the question, our question, whether this L function equals to this expression. Okay, so that much we know, but now we ask whether this is true, that this equals to integral over g over R of the quite similar expression. So it's phi 0. I'm sorry. Okay, it's a spherical vector. Quite similar expression, just instead of this generating function, we have our fg. Okay, and obviously everything will be follow from the fact that these two functions are equal. So it's enough to show then these two functions are equal. Okay? So either this is true or it is not true, but if it's true, then we get it regardless of the uniqueness or non-uniqueness. It works perfectly well for all functionals. And and for all pi. Okay, so now the question is how to treat this equality. So in some cases, when delta rho can be computed for whatever reason explicitly, these are rare cases. But this is, for example, was the case in the first work with non-unique models of PS and Rallis. Here the delta function takes particularly simple form, such that obviously it is being a function, being a power series whose coefficients are in Hecke algebra. It's determined by its elements on the torus, in a positive torus, and on this torus it is just given by a character, basically character in the power s. Okay, so it's
F is some kind of section of an Eisenstein series.
well, in this case, F is section by Eisenstein series multiplied by a Schwarz function from here taken in a certain point. So both sides are quite explicit, and of course it takes time to perform this calculation of this function, but everything is very, very explicit. Okay, so this has been shown. Furthermore, there appeared subsequent works of Ginsburg, Bump, and Furusawa, where they considered other models. In all of them, this function was known, so that they just did a similar thing. In all these cases, this function delta rho was essentially again defined by a character in the power s on the positive torus. So at the moment there is ongoing works of Ngo and Van Weyli for absolutely different reasons, trying to obtain information about these basic functions. I think they try to stick in the trace formula to see some beyond endoscopy phenomena, but they look for the geometric meaning of this equality, and it's obviously exists, but I will not speculate on this because there are not many concrete results. Let me just now go back to my integral and to explain what was the kind of new feature there, and also to state the consequences that we have from this. So I think it's okay to devote last 5 minutes to G2. Okay. So actually the phenomena that I'm going to describe now, it's not very special for the case G2. In fact, Chris Skinner's students, recently completing his thesis, featured the same phenomena for the group GSP6. So the idea that trying to imitate the definition of this delta rho in the case of G2, meaning taking various characters on the torus, doesn't give the L functions. Apparently, this delta rho is much more complicated in the case of G2. So far, then, instead of looking of delta rho, whose Satake transform gives us the L function, we took its closed cousin, who is indeed whose definition is quite simple, namely it is a character on the positive torus. However, its Satake transform doesn't give the exact L function, but L functions times certain polynomial, which depends on pi. Okay, so for G2, I mean, we don't have formula for delta rho. I forgot to say that rho in this case is the standard 7-dimensional representation of G2. G2 is a naturally subgroup of SO7 and hence has a 7-dimensional representation. It's the smallest representation of smallest dimension except the trivial one. So we don't have the formula, and instead we consider it a different function in the same space as delta, such that when we consider its Satake transform, d rho of GS, we get L function, the desired L function, times, unfortunately, some junk. I mean, some polynomial which does depend on pi. However, it depends in a very manageable way. So it doesn't, I mean, the similar phenomenon exists for all the spin group. It's famous Shimura's conjecture. However, this polynomial is of, could be of very high degree, contains like hundreds of terms, unmanageable. However, in this case, it was okay. But from this equality, it essentially follows that d rho equals to delta rho times some polynomial. Okay. Okay, where here p is a polynomial in the Hecke algebra, no longer series, but just polynomial. Okay. So obviously, since the averaging commutes with the convolution, this follows immediately. So instead of showing that delta averaging of delta over R equals to F, we have shown that averaging of D over R equals of this F given explicitly times this polynomial. Okay, so that's we have showed, and this was first step. Quite non-trivial computation. And the second step was just to show that actually the convolution with P is invertible operation. So that we did inserting the whole story into completed C-star algebra and showing that this is this C-star algebra, this is an invertible operation. So from these two things, okay, we got that F equals delta rho R, and this has shown.
That's presumably you have to compute the transform of something of maximal ideal and show it's not zero. I mean, to show this thing's invertible.
To show this thing is invertible, we put all the story into.
Eventually, it's a computation of some transform not vanishing.
To show no, I mean to show everything we just showed that as an operator, this thing has norm 1. Okay, for S big, So this is an invertible element. I mean, it is of the form 1 plus something of smaller norm. Okay. So that's the story, and maybe can I take another 3 minutes? I just want to. Okay. Okay. So just as I said, that beyond getting meromorphic continuation for this partial L function, we can actually get an information of characterize the representation themselves using the poles of this L function. This was an eventual, I mean, when we started this project like 12 years ago, we considered this function exactly in the purpose to characterize certain non-tempered cuspidal representation. So just as a corollary application, I would say. Oh, okay, and yeah, I didn't mention actually that, mentioned in the abstract that all this work, the computation, is joint work of myself and my student Avner Segal. So this is This is his thesis. So the application would be as follows. We can slightly modify our, non-essentially modify our integral here, considering the Eisenstein series induced not just from the trivial representation, but also for a character. Okay, so unitary character. And in this case, we obtain the L function of the twisted L function times this junk at bad places is this integral G2 f of g e of chi gs dg. Okay, so in fact, so also I mentioned just one integral. In fact, we consider here a family of integrals because instead of the initial group D4, we could take quasi-split forms of this group. They are all parameterized by cubic algebras, and starting with the Eisenstein series on the quasi-split form D4 will eventually unfold with the model which is exactly Fourier coefficient with respect to this cubic algebra. So starting with the representation of G2, which supports a Fourier coefficient with respect to given cubic algebra E, we should look at this integral and not the other to ensure that it doesn't vanish. Okay, so then the poles of this L function come from the poles of Eisenstein series, and in fact the residue of this pole have the residue of this Eisenstein series in different points have very nice meaning. For example, if we consider s equals 2, okay, rather s equals 2 here, there is a slight shift, doesn't matter, then the Eisenstein series, the residue of Eisenstein series would be a minimal representation of the group D4. Okay, so the residue of Eisenstein series with respect to corresponding character corresponding to this cubic field is, I mean, when we let the section vary over induced representation, they could admit a pole, and the residue generate what is called pi e minimal representation of D4 E. And hence, we obtain the following theorem. Whenever this L function of pi times chi e, so let me put here, chi e has a pole, then the integral of the cusp form against the minimal representation does not vanish, and so the representation pi is necessarily its theta lift to a finite group scheme defined by E is non-zero. So in this case, so L pi times chi E S rho has a pole at s equals 2 if and only if the integral f pi of g against the minimal representation doesn't vanish, which means that we can consider the centralizer of G2 in this group is some finite group corresponding to E, and so we have that the theta lift of this condition characterizes the theta lift of pi, so theta of pi to some finite group, which I have no time to explain, doesn't vanish. Okay, so this L function condition characterizes this theta lift. The poles of this L function, or rather twisted L function, at other points characterize other theta lift. There is a nice tower property, which is very similar to the tower property that occurs in this case when the poles of this L function characterize theta lift from different orthogonal groups. So I think I'll stop here. Thank you very much.
So in this non-unique model case, is there any hope to get a good local theory? I mean, can you find like gamma factors or?
Well, that's exactly. I mean, that's what's my dream is to do that. How it hasn't been done yet. For example, it hasn't been done in P.S. Raleigh's case. One of the problems is that you don't have the starting point because to define the gamma factor, you use the uniqueness of the of this functional, right? I mean, applying the intertwined operator and looking between the ratios. So here you do not have that. So we should look for the hidden structures to achieve some invariance. I have some vague idea how to do that, but nothing exists at the moment.
What was known about the standard L function in G2 before by any other method?
Oh, sure. Actually, there was a recent progress about this function simultaneously with our work. So first of all, the story about G2 is as follows. In 90, Ginzburg has constructed the L functions for G2 for generic representations only. So this L function, this integral representation unfolded with Whittaker model. And that's what existed till our work. Almost simultaneously with our paper, Ginzburg and Handley performed doubling construction for G2, which is quite remarkable because exactly as in the classical doubling case, we take two cusp forms on G2, okay, but integrated this time not against this innocent E on SP4, but rather on the Fourier coefficient of some Eisenstein series on E8. So there exists a Fourier coefficient whose stabilizer is G2 times G2, and after tremendous computation, which was involving computers and also very, very clever, by the way, computation. So he.
It's all being taped.
I mean, this computation can be checked like by hand, but. So,
do they get the information? Okay, Ginzburg usually never looks at ramified places. But do they get
no, they do not get any information.
Do they get a functional equation?
No, I don't think so. But the point is that somehow, compared to this integral, I think that integral is sort of overcomplicated in the sense that you cannot read the poles of L function from the poles of this huge Eisenstein series because you have many. I mean, looking at Arthur parameters, you can see easily at which poles you expect L function to have poles just from the parameters. But from this Eisenstein series, you see many more. Obviously, when taking a residue, this residue when restricted to G2 times G2, it just doesn't see cusp forms. But it's not easy to prove that. While our integral here, I mean, it accounts for all the poles of Eisenstein series account to some poles of L functions, which could be very nicely characterized as functorial images from. So G2, luckily, it enjoys many functorial maps who most of them are realized explicitly by theta correspondence, and so there is quite a lot of information about it. Okay, yes?
Does your method apply to the spin L function?
The sort of similar method for the spinel functions for GSP4 and GSP6 has been performed by Alan